Good morning. I'm Rob Grasby. I'm part of the product marketing organization here at Juniper, and I'm with Matthew Morgan, the Senior Director of Product Management in our switching business unit. I want to give you guys a little bit of a secret, share a secret with you. We're about to launch a new platform in the next 30 days or so. We're going to share, just a sneak peek at what it can do and address some of the challenges we heard over the last hour or so. As Abner was talking about, the network is code. And one of the comments that was made here is, how do we get to a point where there's an open set of APIs that customers can innovate against? You've got vendors, with different interfaces, but there's no homogeneous approach to automating the network. And what we're looking to do is bring to market a new core switch that is the most programmable switch in the market, not only providing the platform for open APIs, but providing programmable silicon so you can handle future change that we can't predict today in the networking environment. A great example of that would be network overlays. It's driving hardware churn on different platforms. But you can have a programmable ASIC. You can handle this future change. So again, as I mentioned, we have a new platform coming out in the not too distant future. There'll be more information coming available on it over the next 30 days or so. But in the meantime, I'm going to hand off to Massam, and he can give you a deeper dive on what programmability means to Juniper and why this platform is the most programmable switch on the market.
Thank you. Thanks, Rob. So I was thinking about what should we talk about. We can talk about a lot about the speed and the feed, the size of the box. But what really keeps us awake at night is the story that we heard this morning. Everything surrounding us in data center, in campus, in IT is going through transformation. World is changing. And one of the biggest change that we are really seeing is the functions in the network are becoming extremely sophisticated. And as you open up this new API, go to new age of operation, you're seeing that the instruction set that's coming to the network is dramatically different. Have we built our switches for last decade or so to adapt to those changes? Have we really thought about what are the changes that's coming in next 2 to 3 years? I was thinking about last 2 years, being in product management for long enough time, it has been very, very tricky. Because 2 years back, 3 things that was not in our vocabulary, SDN, overlay networking, VXLAN, suddenly popped up. We started looking into it. We started looking into the control plane, the problems it solves. Then we started to look deeper. If we had x86, all our networks built with x86, fully programmable and flexible, we could take these protocols and deliver it to the market very, very quickly. But the reality is, for years, we have built switches and started to deviate from our basic foundation and principles that we used in our routers. Where we, from get-go, we have taken a lot of capability into the silicon, but we also preserved one fundamental behavior in the silicon, which is a way to program the silicon. As it goes out, day one, I'm enabling certain protocols, encapsulation techniques, but as new protocol evolves, and when you have to look at the packet differently or encapsulate the packet differently, I didn't have to go back and turn a line code of my route. So why couldn't we do it in the switches? What I'm going to talk about is some of these fundamental changes that we are bringing onto the table with this new generation platform. Now, we believe with these platforms, we're going to foster innovation from silicon to systems to network and dramatically on the operations side. So as we are talking about core, I wanted to start with 2 sides of the core. On one side, we have data center. The other side, we have campus networks. And a lot of time we see in IT environment, it's a single core that's serving both sides. In one side, I have the production house of information. The other side is the consumption of the information. And if we look at the amount of changes that's happening and the types of need we have, look into the data center side, things are getting more and more virtualized. It started with compute virtualization, storage virtualization. Now it's coming towards the network. things are getting more and more automated. We have automated network for a long time, but now when you glue orchestration and automation together, it's a very different set of automation that we have to deal with. And we start to hear about overlay technologies, and it's not only one option. We have multiple options and protocols to enable overlay. But on top of that, there is a new phenomenon on multi-tenancy. Multi-tenancy in data center is going to create a new set of challenges. So we heard and talked a lot about the control plane aspects of things that needs to happen to make all these things to realize. But then we also started to look into what we can do inside the servers in x86 machines. Then we started to look deeper and deeper. What is the implication on my network, on the infrastructure? What I have to do differently, the things that will evolve in a very different direction moving forward. And then when you started to look into the campus, there are things that's changing as well. In old days, we had a wired infrastructure, then wireless infrastructure came together. Both are very critical today. We cannot live in a world where I have only wired or only wireless. We have to have both. And when you go towards the core, it's a single core that has to accommodate both. Then you start to look into BYOD and mobility. We start to see these phenomena happening in the enterprise side as well on the campus. And then the next wave is virtual desktop. All these things coming together, and if you look at the information flow, it's going to go through the core. Can we be ignorant that all things has changed outside of the core, and the core remained exactly the same as we built it 15 years back? It needs to change. And what are those type of changes? It's not about just adding more bandwidth. It's more than that. So I try to frame it this way. The way we look into the core, the number one piece is to keep up with the growth. When you talk about growth, the traffic pattern as it is changing. You look inside the data center, I have to accommodate more compute to compute or east-west, and I go to data campus, it's more north-south traffic. But on the same time, if I look at the core, I have to connect these campuses together. I have to connect data centers together. I have to provide connectivity between data center and campus. So all the attribute that's coming from both sides has to collapse, and all those functions that's needed has to be collapsed into a single core. Now, when you look into the infrastructure, in one side, you're seeing there are a lot of sophistication coming in through automation. You talk about Puppet or different waves of automation technique. It's extreme sophistication. But those sophistications and complexities oftentimes is not into the network. Your network needs to become simpler. As your network becomes simpler, automation and orchestration is going to become much more easier. So what we will be doing in the core networks is we anticipate moving forward, it's not only just data center. Anywhere in the network, you won't have spanning trees. The world is going to move into all L3 networks as much as you can. Only in places where you need L2 or you must have L2, you might have L2. So you have to build an infrastructure where the core can accommodate L3 connectivity, L2 connectivity, and it's super robust. And the demand, if you look into, I'm building one core that has to support my enterprise campus need as well as data center need, I have to have an option to scale up, scale down, and oftentimes scale out as well. And while doing so, as we bring a lot of functions together and give these options, it will allow us to collapse tiers, collapse functions as people need it. So when you start to look into network functions being collapsed into a networking device, you can think about, I will build an IP-only network or Ethernet-only network. And then you'll go to a point in the network, let's say I'm trying to connect two of my data centers together. You have to bring in MPLS function and collapse it. The other option is I will keep on building multiple networks and stitch them. Instead, you can bring all these functions into a single network element and simplify it. So it's not only IP and MPLS. You have to bring in MPLS technologies, and it's all standard-based, MPLS, VPLS, you name it. And on top of it, when you put overlay networking in the physical network, the overlay world, it needs to be someplace in the network where the overlay technology comes and goes down to underlay. The assets in the underlay has to talk to overlay and vice versa. So these are all things that needs to happen on the core. But more importantly, this is not the end. We believe this is the beginning of a new journey, looking from the core. So how do we foster innovation? changes that's happening on the endpoint, access layer of the network, the endpoint of the network, wired or wireless, with SDN, the amount of change that is possible, with programmability, the type of sophistication that your app guys, your compute guys are going to demand for, can we accommodate those changes in the core? Now, the way we look at it, very simply speaking, networks are going to get simpler, and what we will put on the bottom is a single element. It's a core. It can function either in your campus or data center, or it can combine your data center and campus together. Now, what is this core? It comes in different form factors as we built our switches, 2-slot, 4-slot, or 4-slot, 8-slot, or 14-slot. It's extremely scalable, flexible, and programmable in nature. So let's go through it very quickly. What is this programmability that we get? So Jeremy talked about the APIs that we are going to expose, Puppet and few others. So these are the APIs that we are adding on top of the automation toolkit that we already have. You can already come and talk to our switches using XML or netcode. But now we are going to open up more sophisticated APIs to interact with them. And then when you go deeper, you look into the building block of this switch, the ASIC itself. The magic is on those ASICs. That now you have an option to go and program that ASIC. Do we expect that our end users to go and program those ASICs? Not really. We have to do it. But all the interfaces, the outbound interfaces are going to be programmatic APIs, and we're going to provide these middle layer and quickly adopt new technologies as it comes along. The logical scale in this system is big, and for a reason. If you look into virtualization, one of the angle, or if you look into desktop virtualization, the endpoint in the network is going to expand. As a result of that, your MAC table, the route table, has to scale. There's another interesting phenomenon as you start to look into programmable APIs or attributes like OpenFlow. This is where I'm going to spend a little bit more time as I go to the next slide. That when you're trying to optimize and fine-tune your network with a flow-based schema, that flow table in your system needs to be very different than how it is today. In most of the switches that you have built in previous generation, we used to have our FIB table, MAC table in the order of 100 and multiple 100,000 of entries. You look into the forwarding table, the filter tables that we typically use for OpenFlow had been very constrained. In the access layer, it has been in the range of 3,000, 4,000 filters that you can put, or flows you can accommodate. You go to the aggregation or core, it has been in the order of 50,000 to 100,000. Now, if I really want to make a meaning out of this programmable attribute and flow-based attribute that can come from northbound, in the system as well, I have to scale number of flow state that I can manage. So this is one of the key assets that we had to put into the silicon. If you look at it, it's 256,000 ACL or filter rules that you can put. And that can be programmed directly by OpenFlow, for example. And on the feature side, it has all the existing layer 2 features, layer 3 features, and a lot of new protocols that I'm going to talk about in a minute. So as we look forward, how this system fits into your network and how we're going to enable automation and foster innovation. So let's start from a network view. When I look the next generation core in the context of a network, it's going to provide you a network abstraction northbound. And the objective of that network abstraction is to talk to orchestration systems. Who are those orchestration systems? So if you think about a virtualized data center environment with VMware, VMware is going to orchestrate the endpoint. And if you think about an OpenStack environment, that's the orchestration layer orchestrating your compute and storage. And then with the OpenStack plugin and VMware plugin, that's sitting on top of my network is going to enable all the network orchestration from a single pane of glass. This is one part of the work. It will really help us to innovate our workflows and simplify workflows. But the next step really goes a little deeper into the system. So when you go to the system level, now you're interacting directly with the system. You don't have the complete network view. If you desire, you can get the network view, like read the BGP state table, and you can get the global view of the network. But you could directly go to the box, either through Puppet, you can automate things, or you can have OpenFlow API directly interacting with your switch. And then you can also get a little bit more or sophisticated by interacting with the box using Python. Now, the piece that becomes really, really interesting is when you have this interaction with the box, that's like user is interacting with the system using these sets of API, and they can ask for a lot of sophistication. How do I provide those capabilities in the silicon? If I don't, what will happen is, let's say I started to innovate using OpenFlow. I'm demanding my flows to be monitored and steered using OpenFlow, and suddenly what you will see, your flow table that we usually have in the system is going to be exhausted. You cannot really get benefit out of it. You have to really think about how this is going to map into the silicon that you have. The second piece is, in real life, if you are trying to foster innovation in your network, are you going to build a brand new network to try new things? Or are you going to have a network that serves your purpose today? All your existing apps and infrastructure works as is, but on top you're going to create a pseudo layer, a virtual network per se, and virtual assets that's controlled and contained. And when needed, you can allow your traffic to move from one layer to another layer. So this is very critical in our view, that how do we enable these capabilities on the same time I can support today's infrastructure. And that's something you cannot just do it in the software layer. For example, when you're dealing with Python, and you can talk more about it, that if a Python or Puppet is coming and operating your network. So now you have two operators that's interacting with the switch. One is your network administrator, who is really managing the infrastructure, full knowledge of the network topology, full knowledge of what's happening on the route tables and so forth. And then there is a lot more ephemeral state that's coming from Puppet, for example. This is the access part of my infrastructure. And they're going to oftentimes compete for resources in my system. Just think about filter rules, ACLs. If I have 5,000 entry in my ACL table, up front I should be deciding how much of those ACL entry is going to be preserved for my infrastructure and how much is going to be preserved and allocated for the ephemeral state. And that resource allocation has to be done up front. When you do that resource allocation, it's not only in the software and the control plane, you also have to have capability to do it in the hardware. Just like what you do in server virtualization. When you create 3 virtual machines, you're going to give resources. The memory and the CPU is going to pin down for each of the virtual machines. So as you go deeper into the system, from system into the silicon, that's where the connection is going to be. So when we go deeper into the silicon, number one attribute is providing the meaningful tables at scale and have the capability in the system to lock and isolate those tables. So I should be able to have an ACL table or filter table that is divided into multiple groups, and there are multiple users from software. The second thing is, when I have some of these meaningful tables, like the filter tables, they have to scale. They have to scale proportionally to the FIB table and the MAC table that we have in the system. Then it becomes a little bit more interesting as we move forward. So think about VXLAN and NVGRE is something that we think we will be doing. The protocol stack, the control plane is all maturing. So within 1 year, these are the protocols that will come into our network. We'll see VXLAN, we see NVGRE, MPLS over IP, all is going to ride on my network. And now, when I go to the switch, from the top layer, we're going to say I have some VXLAN segment, some NVGRE segment, some MPLS segment, all coming together. On the same time, I have my old VLAN segments as well. So I have to figure out a way how I create a bridge between all these new technologies. And while doing so, I should not be required to go and replace cards. I should not have a need to go and put a VXLAN card, a MPLS card, a NVGRE card. It has to be more programmable. And as you program it in the silicon, you should not sacrifice performance. So what's in the Junos 1 custom silicon is a very different pipeline than what we used to build. And that's what I'm going to talk about in the last 5 minutes on the whiteboard. Does it make sense? So Jeremy talked about this layer. It's very exciting. This layer he didn't touch. That you have all this flexible way to come and instruct the box to do something. Here I had a silicon. I had line card or a switch. And that was built with the silicon. And the silicon looked like this in very simple terms. It is a fixed pipeline chip. I had a parser. And then after parser, I had filter logic. Then I had lookup and forwarding logic. Then I had queuing logic. And then finally, I will rewrite and send things out. And then the instruction set that's coming from here is eventually going to talk to one of these entities. The way we used to build it is we had a parser, and that parser was built for, let's say, layer 2 switching. And then we built it for layer 2 switching and layer 3 switching. Then we built another parser that could do MPLS. But we really, really loved it. We said this parser has these 3 options to do things, right? I could do MPLS, I could do IP, and I could do VLAN. Next day you come and say, I want to do 2 things together. What would happen is, well, this parser can't support it anymore. That will be the answer. And those are the times in last 15 years or 10 years history, what you have seen is something new came in the industry. After 2 to 3 years, you saw a refresh in our switches. We refreshed the line card. The purpose was I had to go and rebuild this chip to accommodate that new thing. Then you go to the filters. Again, those rules are predefined. You pretty much locked it, and oftentimes you gave enough options and anticipating what are the possible things that's coming in the pipeline. And what becomes a lot more complicated is the rewrite function, because this is a very expensive operation in the chip, that you have to now go and find a place in your packet that's passing through at very high speed. I have to rewrite. Oftentimes, I have to inject something if I'm doing encapsulation, decapsulation, and tunnel termination. So in these fixed pipelines, anytime a new protocol came in, protocol in a sense that needed something to be changed in the packet header, it forced us to go and build yet another silicon, and innovation slowed down. Now, with the silicon set that comes with the next generation core, has a lot of flexibility on this layer and this layer. Flexibility means the parser that we use is a programmable parser. User can go, and in this case, user being us, and we expose it to you through this, and we define a new instruction set. Now this parser has to go, instead of looking at specific field, you're going to say, I want to look at 150 to 160th byte. And then there is a match engine. That match engine is going to say, this means this encapsulation. And then I can also go and tell my lookup tables and filter tables to make decisions based on those new parsed data. And today what we do, we use microcodes to do it. And microcode is something hidden underneath. And what we expose out is through these XMLs. And then you can use your Programmable API to really see what's happening. Then when it comes to rewrite, this is where it becomes more challenging and interesting. For example, when VXLAN came along, and this chip was not, it was already designed at that time. NVGRE came along. The design phase was done. We're about to go into production. But for us, being programmable, what it allowed us to do is, it's a little bit of microcode. Now, I can also do VXLAN. I can also do NVGRE. Encapsulation, decapsulation. On the same chip, I can have some traffic flowing with VXLAN, some traffic flowing with NVGRE. At the same time, I have MPLS traffic coming in. I can parse them all together and route traffic in between, bridge traffic in between. This is super powerful as we started to make these engines programmable in the chip. So net, what we are doing with the next generation core is all the programmable attribute that we are seeing from the top layer. As we push it down deep into the chip, we are extending it down. The first wave, we are not going to expose, it's quite complicated. How to program our chip is going to be kept in Juniper. We are going to provide those shim layers. We are going to write microcodes. But we also believe that with the advancement of the API, northbound APIs, we will be able to get to a point where some of our partners could even go deeper and program for our chip as well. With that, I would like to get any questions that you might have.
So are you talking? So when you say chip, are we talking merchant?
No, it is Juniper custom chip. And this is something, if you look in the merchant world, this is where merchant has been, and this is how you will see from merchant. Fixed pipeline silicons.
So still down ASIC as opposed to FPGAs, NPUs.
So yes. So if you look into doing things into FPGA today, right? To get a fast pipeline with reasonable latency and reasonable power, you need a lot of space, a lot of power to do things in FPGA. And programming in FPGA is super difficult. So the chip that I talked about here, this is a 120 gig pipeline. It's doing everything. It's not like I'm putting an FPGA doing one function. It's doing everything, and you have the complete knowledge of the pipeline. When you do things in FPGA, the problem becomes that I don't have the complete knowledge of my pipeline. The decision that I make here, how do I propagate that decision to the very last step? In FPGA-based system, that becomes extremely challenging. Instead of doing it in FPGA, or if you look into the NPUs, NPU had this limitation of getting enough bandwidth. Here, it's not NPU, this is not FPGA, but some part of the pipeline is programmable inside the chip.
Are we going to talk about it? Because I liked your original slide that had, here's all these edge functionalities, here's the core. I mean, what you're really kind of defining is this hybrid mechanism that somebody needs to define, and I think it's going to come out of the customers rather than coming out of the
We believe what's happening in the industry today, especially with new encapsulation techniques as well as overlay techniques, this placement of this function in the network is going to evolve. We'll see some sets of customers who might want this function to reside only on x86. There'll be another set of customers, they would need it in x86 in server, as also in access layer. But when you are trying to build an exchange where I have multiple of these segments come together, then you have to push it towards the core.
Yeah, I just think, so the problem is at the edge right now, it's classification, and then I don't care what we go into, right? Go into a tunnel, go into an LSP, who cares? Because as you aggregate up, if you're doing, I think flow-based forwarding is layer 4. We're talking about application awareness. We're not going to get there without layer 4. So we're starting to combine some of that functionality. But it's that ingestion where, like, to your point on scale, right? Really, it's not this huge problem, I don't think, because we're going to distribute that out all over the edge, right? So we can just.
So I will give you one sort of paradox that we are living in. If you try to distribute in your access layer, let's say top of rack switches inside data center. In the top of rack switches, if you go to the merchant world, what is the size of your filter? Best option that we have in the market today. It's about 4,000 entries.
Oh, yeah.
And if you really use the hash efficiency, you can get 3,000 entries.
Yeah, no, that's probably closer to 1,500, 2,000. Yeah.
Correct. So how do you scale it? Even if you distribute, then it becomes quite different.
Current generation, right? We're retrofitting stuff. There's, we've got three TCAMs to work with, and we're using one of them.
Yes.
Right? But I mean, I think the hardware will change and become a little bit more flexible. And it doesn't take a lot to do things like traffic screening.
Right.
I mean, we've kind of had this conversation a lot, so I'm not going to beat it up. But
So we believe that it will.
At the beginning, I think
it will get better in access layer, but the core of the network also needs to have this awareness, especially when you have to make aggregated decisions, not granular decision, but when you come to a point that I have one domain of control, another domain of control, right? they come together somewhere in the network. That is the core, and that's why you have to have these type of functions as well.
Yeah, I mean, so cross domain. I mean, it's probably the hardest problem of all this, and that should be absolutely. I mean, we shouldn't expose TCAM to.
Right.
Akamai's not gonna expose their TCAM
Correct.
to Verizon, right?
Correct.
I mean, but that's out to whatever.
And that restriction and sort of enforcement cannot be just in the control plane. You should think about how do I go deep and preserve those resources down into the hardware level. Just like what server virtualization warrant has done. Any other questions, thoughts?
Is there an architecture document?
So a lot of the collaterals are going to be available within next 30 days, including architectural frameworks.
Yeah.
Good. I like those.
Yeah.
I learned lots from them.
If not, thank you.
Thank
and
you.
I'll hand over to